What's up, everybody? Let me get this set up. Alrighty. No, not that. Okay. So let's get going here. Let's come into Notability. So I know where I'm at, right? Yeah, I did those. Hmm. Did I do that? Yeah, I did do that. I didn't do this one, though. So this is the next one to do. Oh, I can check my photos. Right, so that was the last one I did there. Last one I did with Calc was that one. Right, so we did that and we did that and that was it. Last one we did that was there. Okay. So, oh, is my pencils connected to this one? No. Wow, I am not good about connecting my pencil. So let's do that. And see if it's charged. Wow, it must not be charged because it's taking so long to connect. Weird. That one connected. Can I see the battery life? Ooh, that battery life is nothing. Hmm. Yeah, that makes sense. Well, we'll charge it for a second. Honestly, that's a pretty solid charge on it. Let's use that charge until it goes out. Alright, so hopefully the iPad screen goes back up. Nice, it is. Okay, so that is where we are in that one. Where we were in this one. Oh, nice. I did circle where we were in this one. Right, because that was the last thing we did. Okay, yeah, that makes sense. Alright, so let's start with Algebra 2. So we're going to grab the problem, come back over to here, delete it, put the new problem up. Make it way bigger. Alright. So take a screenshot. So this is the one just like the one before. So how do you solve this inequality? Well, it's got absolute value, so you've got to split it up into its two different equations. We're going to have that 2x plus 4 is less than or equal to positive 3, and then also the negative version, that 2x plus 4, and then remember negative, so we got to flip the sign, negative 3. So there we go. So now we just got to solve both of these things. So we'll subtract 4, 2x is greater than or equal to negative 7 halves, and we'll divide by 2. Oh, wait, whoops. That's just 7. Got ahead of myself. This is negative 7 halves, because then we divide by 2. So we get that x is greater than negative 7 halves. Or, over here, subtract 4, 2x is less than or equal to negative 1. Divided by 2, x is less than or equal to negative 1 half. And so you see we have two things here, two inequalities. And we don't know, we have to decide, do we need both of those inequalities to be true? Or do we need just one of those inequalities to be true? And that's going to come in up here. So if it's a less than sign, then we need both of them to be true. It's an and situation. But if it's a great or sign, then it's an or situation. We just need one of them to be true. This one is the absolute value is less than 3. So that means we need them both to be true. So let's look at these. So we're going to have, let's see, where did they even go? So you want the bigger number on the right. So that's actually negative 1 half. Negative 7 halves is less than, so it's on the left. And think about what we have. We need it to be greater than negative 7 halves and less than negative 1 half. So what we're saying then is it has to be in between those two values. So you see our set of solutions is right there in between the two values. And then there's an equal to sign. So when we're deciding open dot or closed dot, we want to do a closed dot to show that it is allowed to be equal to those two numbers. And then the last thing you might want to do is write it in interval notation. So what is this in interval notation? Well, you've got from negative 7 halves to negative 1 half. And it is allowed to be both of those things. So we'll put a bracket on it. So there we go. Interval notation, anything from 7 halves to negative 1 half. And I guess the last thing we might want to do is combine these two inequalities. Because I really like writing answers like this and seeing answers like this. That it shows that x can be anything between negative 7 halves and negative 1 half. Alright, good stuff. So let's delete that. And come back over here. So the next one is a great or problem. This is still a less and problem. So here we got another inequality that is absolute value of 1 minus 4x is less than 5. So just like before, the first thing we got to do is we got to split it up into its two different equations. That 1 minus 4x is less than positive 5, or 1 minus 4x is greater than or equal to negative 5. And then we can just solve both of those out. The thing to remember here is that we're going to have to divide by a negative again. So when we divide by this negative 4, we've got to flip that sign around. And then the negatives cancel, simplify the fraction, so x is less than 3 halves. We'll do a similar thing over here. Subtract 1. Negative 4x is less than 4. Oh, this isn't less than or equal to, though. I wrote that wrong. Just less than, and then we divide by negative 4, so x is greater than negative 1. And so here, it's a less and problem because of this sign right here, that our absolute value is less than 5. So we need both of these things to be true. So when we put it on a number line, we need it to be bigger than negative 1 and less than 3 halves. So what is our answer? Just right here in between those two numbers. And in this case, it's just less than, it's not equal to. So we've got our open dots. When we put it in interval notation, we use parentheses from negative 1 to 3 halves. And lastly, just as a combined inequality, negative 1 is less than x, which is less than 3 halves. That x is in between -1, and 3/2. So absolute value, the gist of it is you split it up into its two different equations. And then when you have two equations, you've got to look at this sign right here. Is it less and or great or? And that'll depend on if you need both of them to be true or just one of them to be true. All right, good stuff, good stuff, good stuff. Oh, I need to slunch my shoulders a little. I have been feeling a lot of stress in my shoulders. All right, so let's delete this. Let's go to here. And let's do this one. So we got another inequality with absolute value. But this time, the absolute value has to be greater than 3. So we're going to start it the same way. Split it up into its two equations. That x is greater than 3. X is less than -3. And here, since this is a greater sign, we don't need both of these to be true. We just need x to be less than -3 or x is greater than 3. And when we see this on a number line, that's a good thing, because these two, in this case, actually don't overlap. Because you see greater than 3, less than -3. But luckily, we don't need them both to be true. We just need one or the other to be true. So that's going to give us our two sets of solutions. Less than -3 or greater than 3. And so when we write this as an interval notation, it'll be similar, but we're going to have two different interval notations because there's two sets that x is allowed to be in. It can be anything from -infinity up to -3, or union, that means or 3 to positive infinity. Parentheses on all of them because it's just less than and greater than, not equal to. So it can't be 3 or -3. But there we go. So it's the same idea as all the ones before. You split it up into its two equations, and you got your two inequalities. But if it's greater, you just need one of them to be true. The other ones that we've done so far were less and. We needed both of them to be true. But here they don't overlap. You just need one of them to be true. All right, good, good, good. So let's delete that. Let's come back to this one. Here's another inequality with absolute value. So what are we going to do? We're going to split it up into its two separate equations. 2x minus 5 is greater than 3. 2x minus 5 is less than -3. And then like before, we're going to solve both of these equations. So we're going to add 5 and divide by 2. So x is less than 1. We're going to add 5 and divide by 2. So x is greater than 4. And then we look up here and we see that this is a greater sign. So we just need one or the other of those inequalities to be true. So I do like to always look at this on a number line. We got 1 here. We got 4 here. We need x to be greater than 4 or less than 1. So then you can see our interval notation. It's going to be from -infinity up to 1, not including 1, or from 4 up to infinity. So there you go. Same as all the rest of them. All right, good stuff. So that's our 4. Is 2 videos a day just too much? It's really not. It really should be 2 a day. I mean, what has this been so far? This has been 15 minutes and I've knocked 4 of them out. Yeah, I should be able to post 2 videos a day. I just need to stop getting behind. I need to whip out more. But that's 2 days. I need to start, but I need to do it every day. I need to come on and I need to make these every day. That's really the gist of it. Like, because I can sit down, like, no problem and whip out 2 of these. And it needs to be consistent. I need to be coming on here right after Math Lab. Yeah, I should be doing that right after Math Lab. So at like 9:30, 6:30 my time. Come on here for like an hour, go to 7:30. Yeah, that's what I should be doing. Alright, so let's do some calc. We're going to try to do 4 calcs. So that's what I should be able to do. I should come on here every day. And I should just do 8 of these problems. I guess, should I set these up earlier? That's what I could do. I could set these up earlier. That'll make this a lot less painless. And I could do that not at my desk. Because that's one of the biggest reasons I don't like streaming, unfortunately. I don't like sitting at my desk. I like to be outside better. So I could get all these set up outside. And it's not like it would make it any harder. And then I just have them all in a folder. Yeah, I think that's what I need to start doing. And then the title would be too much. I don't need to do the title. Alright, I don't remember if I screenshotted this, so let's do it again. Okay. Discuss the intervals on which each function is continuous. Alright, discuss the interval on which each function is continuous. So, we're just going to think of the graphs, and we're going to do some various things. So, this is not a simple thing necessarily. So, A, when is the graph of tangent continuous? Well, we ought to know what the graph of tangent looks like. I forget a little bit. But so the tangent of 0 is 0. But then we know it comes up with an asymptote and it's undefined at pi over 2. Right? Because the tangent of pi over 2 is the sine of pi over 2 over the cosine of pi over 2, and the cosine of pi over 2 is 0. So that's undefined there. And for the same reason, we have another asymptote here at negative pi over 2. So see, what happens is every pi we have an asymptote, but it starts at pi over 2. So let's first write that x is not equal to pi over 2, but then from there, every pi, there's an asymptote. So plus n pi, where n is just an integer. So that's what you do. So see now, like if n is negative 1, it's going to be pi over 2 minus pi. That's negative pi over 2, so that's that asymptote. And that'll clock in every single asymptote. So that's where it's not defined. But I'd like to say where it is defined, where it is continuous. So how can I write that? I mean, let's just look at this right here. So this is from negative pi over 2 to pi over 2. But then where's the n? I guess then it's just plus n pi plus n pi. That's a good way to write it, right? So it's from pi, when n is 0, it's from negative pi over 2 to pi over 2. When n is 1, it's from pi over 2 to 3 pi over 2. So yeah, that'll cut it. You got parentheses because it's asymptotes. Yeah. That's a good way to write where that is continuous. Okay, so the last one, well, the next one, sine of 1 over x. So sine of 1 over x is definitely continuous, except for at 0. But at 0, this function, at 0, it's equal to 0. So the question to see if it's continuous is, as the limit as x approaches 0 of sine of 1 over x, does that equal 0? Because if it does, then it's continuous. But if it doesn't, then it's not continuous. And I'm thinking it doesn't. I'm thinking that limit does not exist because of the oscillation type of stuff. Because you think, Yeah, I mean that's not continuous. That's the one that oscillates infinitely, right? Because if you have like the sine of point 0.1, that's if it's like if x is point 0.1, then it's like the sine of 10. If x is 0.01, it's the sine of 100. So it oscillates faster and faster as it goes to the middle. So that limit does not exist. It does not equal that. It equals d and e. So this is continuous from negative infinity to 0 and from 0 to infinity, but I don't think that's continuous at 0. We're definitely going to check these answers, by the way. Now, this one, on the other hand, I do like this one. I do like this. Because this, the limit as x approaches 0 of x times sine of 1 over x. I do like that is equal to 0. I like that that's equal to 0 because as we plug in things closer to 0 here, that's going to make the sine of 1 over x not matter anymore. So even though the sine of 1 over x is going to oscillate infinitely, that multiplying by x is going to hold it in between there. And so I really think that one should be continuous from negative infinity to infinity. So I'm kind of curious, before we look at the answers, let's see if I can look at the graphs and see if I agree with my answers. So if we look at sine of 1 over x. Yeah, see how that oscillates infinitely. That's not going to approach anything. But when you multiply it by x, see now it is quite clear that it is approaching something. I think that's quite clear that that's approaching 0. It's oscillated infinitely, but that's clear that that approaches 0. So I'm down for there being a hole there, but the hole is filled by the second part of the piecewise function. I'm confident with those answers. Let's see what they have to say. So here, yeah, they did that. They didn't do it in interval notation, so I one-upped them on that. So we got it right for A. For B, because 1 over x is continuous up to 0. Yeah, so G is continuous from negative infinity to 0 and 0 to infinity. Yeah, so we got that right. C, h of x is continuous on the entire line. Yep. And then there's our graphs. That is beautiful. Love getting answers right. Okay, so let's go to... Ooh, intermediate value theorem is next. We'll want to read the answers for this to make sure we show everything that we want to show too. Okay, let's zoom in. So intermediate value theorem, so basic, it's wonderful. So what is the intermediate value theorem? The intermediate value theorem is a very obvious theorem, so don't get it twisted thinking it's difficult or anything. Here's like a real world example of what it is. So here's my pencil. My pencil is right here. Call it a foot, 12 inches above my hand. When I drop the pencil, it's now in my hand. Now it's 0 inches above my hand. So if it went from being 12 inches above my hand to 0 inches above my hand, was it at some point 6 inches above my hand? Well, obviously, right? Because it went from 12 down to 0. So at some point it was 6 inches above my hand. At some point it was 7 inches above my hand. At some point it was everywhere above my hand. It's going to hit every single point in between that 0 inches and 12 inches. And that's the idea with the intermediate value theorem. So what we're going to do is we're going to say, oh, my pencil died. Okay. Well, we have to restart this then. That's unfortunate. Can I charge my pencil like that? It's not even worth trying. We'll just unplug for a little bit. We got a few more problems to do. Oh, and I can't even make these without the pencil. It's unfortunate. How y'all doing? Is anybody over here on TikTok? Oh yeah, what's up, y'all? The live you needed? I agree. You should probably watch on YouTube. That'd be better on YouTube. You see, this is just like a stream of YouTube. Back in action. Get the iPad screen back. Okay. So the intermediate value theorem. What does the intermediate value theorem tell you? Well, it's very basic, actually. So here's what it tells you. So imagine I have this pencil. It's about 12 inches above my hand. And then I drop it. So now it's 0 inches above my hand. Well, so the question the intermediate value theorem asks is, if it went from 0 inches above my hand, no, it went from 12 inches above my hand to 0 inches above my hand, was it at some point 6 inches above my hand? Well, it has to be, right? If it went from 12 inches and it just dropped down to 0 inches, at some point it has to be 6 inches above my hand. And at some point it has to be 3 inches above my hand. And at some point, if it's going from 12 down to 0, it has to be all of those numbers at some point in between, because it's not teleporting, it's just going straight down. And that's what the intermediate value theorem tells us, that if we start at one place and go to another place, as long as it doesn't teleport, as long as it's continuous, it's got to hit every number in between. And so that's what we're going to do here. First, we're going to say, is it continuous? Well, it's a polynomial, so polynomials are always continuous. That's just a thing. So it is continuous. So then we can actually use the intermediate value theorem. So what we're going to do is we're going to say, okay, what is f of 0? What is the function when x is equal to 0? Well, you plug in 0 to the function, you get -1. What is f of 1? Well, you plug in 1 to the function. So let's see, 1 cubed is 1, plus 2 times 1, minus 1. So you get 2. So look at what that's saying. So that's saying at one point, at first, it's at -1. Let's actually draw this. So when x equals 0, it's at -1. And when x equals 2, or when x equals 1, it's up at 2. And what we just said, like it's not teleporting. This is a continuous function. So this graph has to just go in between them. And so what they ask, does the function have a 0 somewhere in between there? Well, it has to. Like, we don't know that the function looks like that necessarily. The function could go crazy. The function maybe looks like something like this. So there might even be more than 1 0. But we know that there's at least 1, because it has to go from -1 to 2. So if it's going from -1 to 2, at some point, it's got to cross 0. That's all the intermediate value theorem is telling us. The intermediate value theorem is important. It's definitely important. It's just not that complicated. But I don't think most of calc is that complicated. Oh, and that's the end of that section. There was only one problem by intermediate value theorem. That's crazy. All right, how many calc problems was that? That was just 2. So we got 2 more. All right, let's get into the next section, infinite limits. Determine the limit of each function shown on the graph as x approaches 1 from the left and the right. Okay. So I remember doing this section on infinite limits. This is pretty much, this actually is the exact textbook that I used when I took this class. Same version and everything. And I remember coming into this, I remember this happened a lot in calculus actually. And I was just like, why is this a new section? This is the same stuff we've been doing for the entire year. And I think that applies here too, because we're just taking the limits. The rules of the limits don't change. It's the same idea. So as x approaches 1, as we're just saying, yeah, as x is closer to 1, what is y getting closer to? So this next section is about infinite limits. And the thing about infinite limits is that they're really not any different from other limits. It's just that infinity is involved. But that's not that scary. So with this first one, well, what does it say? Determine the limit of each function as x approaches 1 from the left and from the right. So here's our x equals 1. So let's go ahead and use the proper notation. So as x approaches 1 from the left of f of x, what do we have? Well, as x approaches 1, you look at the graph from the left side, it's going up. So it's going up all the way to positive infinity. So I don't know if this is like legal to write that it's equal to infinity, but I'm going to do it anyway, because the limit as x approaches 1, as x gets closer to 1, what is y getting closer to, from the left side at least? it's getting closer to positive infinity. And actually, just the same, from the right side, the limit as x approaches 1 from the right side, it's also infinity. Because you look at the graph, as we come in from the right side and we follow the graph, it also goes up to positive infinity. So we're saying as x gets closer to 1 from the right side, y is getting closer to infinity. Y is going up. And so kind of it's legal, I would say, that it's totally proper to write the limit as x approaches 1, just in general from both sides, is equal to infinity. Because look how, as you approach 1 from both sides of this function, they're both going up. So again, I don't know, I don't really think it's totally proper to write that something's equal to infinity, but I'm down for it. It's both going up to infinity. I like it. Now it's different on the next one, because you see on the next one, on the left side, as you approach 1 from the left side, it's going up to positive infinity. Let's see, this is the other f of x. But as we approach 1 from the right side, as we come in this way, it's going down to negative infinity. So here you couldn't really say that the limit as x approaches 1 is anything, because from one side it goes up to positive infinity, the other side it goes down to negative infinity. You can't really say directly what it's approaching. But it's perfectly cool to say from the left side and from the right side what it's approaching. Alright, so that's one flavor of infinite limits, where the answer is infinity. I wonder if the next flavor of infinite limits, or the next example shows the next one. Determine all vertical asymptotes. No, it does not. This is just like a pre-calc question. So find all the vertical asymptotes. That's something you do in pre-calc. I think we're just doing it here to see how it relates to limits. So determine the vertical asymptote of A. Well, what are vertical asymptotes? When the denominator is equal to 0, because that's when it's undefined. So here there's a vertical asymptote at x equals negative 1. And like I guess we could say that because we can see that the limit as x approaches 1 from like what, the left side? Is that positive or negative infinity? So if we plug in a number just less than 1, so say like, oh, negative 1, just less than negative 1, that's important. So say like negative 1.1, are we going to get a positive number or a negative number? So let's just look real quick. If we plugged in negative 1.1, we're going to have negative 1.1 plus 1. So that's a negative number. And then times 2, 1 divided by a negative number, that's negative. So since when we plug in negative 1, plug in a number just less than negative 1, we get a negative number. We know that that's going to be negative infinity if we look at the graph. So if we try to picture this graph, we have our vertical asymptote here at negative 1. On the left side, it's going down to negative infinity. Versus on the positive side, well, first off, since we know it's approaching infinity at all, then it's an asymptote. Then it's a positive, then it's a vertical asymptote. That's like what is going to define vertical asymptotes, I guess. If like as x approaches that number, it goes to infinity or positive infinity, that's a vertical asymptote. And we already knew that anyway from pre-calc, right? But let's just look at the other side. If we plug in a number just bigger than negative 1, so like negative 0.9, well then when we do negative 0.9 plus 1, we get a positive number. And do the whole thing, we end up with a positive number, so that means that's positive infinity when we plug in negative 1. And that makes sense, because as you remember from pre-calc, this is a single multiplicity asymptote, so we expect them to be going different ways. And that's what that graph looks like, roughly. So what are the vertical asymptotes? Well, we said that at the beginning, just that one. And then B, we're going to similarly do that very quickly. We just need that to not equal 0, so we add 1 and square root both sides. So we have our vertical asymptotes at x equals plus or minus 1. And if we want to sketch out the graph real quick, just because that's kind of fun. So we've got our 1, negative 1. And so what is this? I mean, we could plug in a value just bigger than 1. So if we plug in like 1.1, do we get a positive or a negative? Well, 1.1 squared is going to be bigger than 1. So that's where I'm thinking right here. So when we do 1.1 squared minus 1, that's going to be positive. So overall, that'll be positive. So we know it looks something like that. And then just again, back to pre-calc, we know these are single multiplicity asymptotes. So we know the rest of the graph has to look like that. And then cotangent. Cotangent's like tangent, but it's 1 over. So it's going to have all those vertical asymptotes. It's got the vertical asymptote. So let's just picture the graph first. So this one's actually undefined. It's got its asymptote at 0. But then it's got its 0 at pi over 2. So it's going to be like that. So this one has the asymptotes every pi as well, but it starts at 0 here. So its vertical asymptotes, we can just say pi n, where n is an integer. Because then, just like before, so we have an asymptote at pi, at 2 pi, at 3 pi, at 4 pi, at 0 pi, at -1 pi, at -2 pi, and so on. We got a bunch of vertical asymptotes. And the thing about all these vertical asymptotes, like we could say here, if we're looking at this f of x for c, the limit as x approaches, what, pi, it does not exist because it goes to infinity. So yeah, vertical asymptotes, that's not hard. That's like you did that in pre-calc and algebra 2. All right, that's the quota for today, right? That was 8. Was that not? 1. Is that only, we got one more? Yeah, we got one more. Or did I miss a screenshot? Let me see, we did that today. No, that was the first one we did today. Okay, so we got one more. Good, I want to limit as x approaches infinity 1. Oh, geez, determine all the vertical asymptotes. All right, determine all vertical asymptotes. This is a pre-calc question. Not sure why it's here. So remember back to pre-calc. Like, so the vertical asymptotes are when the bottom is going to equal 0. So you might look at it and say, like, all right, we might have 2 because after we factor it, we'll have 2. But again, you did this in pre-calc all the time. Remember, like, what's going to happen is when you factor the top and you factor the bottom, one of them is going to cancel out. So in this case, 2 is not a vertical asymptote. So we're going to have a hole at x equals 2. But since it canceled out, that's not going to be a vertical asymptote. Our only vertical asymptote is going to be x equals -2. And you think back to limits of how these limits always work. Like the limit of this function as x approaches 2 of f of x, it exists. We can actually say what it's equal to. Because now that we canceled out the x minus 2, we can just plug in 2 and see that it's equal to 6 over 4 or 3/2. So since the limit is defined at that x value, there's definitely not a vertical asymptote there. However, as x approaches -2, we see that's still a problem. Because even after you simplify it to be x plus 4 over x plus 2, you still can't plug in -2 into there. And there's no way you're going to make it to where that is going to be able to plug in -2. And that's because there's a vertical asymptote. So this limit does not exist. So that's just, I mean, that's important to remember, but you know that. You remember that. You got to factor and you got to find the holes. Because just because it's on the bottom, it might cancel out. And if it cancels out, it's not a vertical asymptote. It's just a hole in the graph. All right. So I think that's all I got for you all today. But that was fun. We got 8 of them. That's 2 days worth of videos. So hopefully we'll be back here tomorrow to make some more. I'll see you all then.